semester, and we're going to talk about altitude. Okay, so again, we'll start off with acute responses and then finish with chronic responses. So here are the outcomes for this lecture. So when it comes to altitude, it's important to know that just being at altitude doesn't really have any effect. It's not the fact that we're at 5,000 or 10,000 or 20,000 feet. The issue is that the air pressure itself changes. Okay, because there's less air the higher up you go. And we refer to this as hypobaria. Okay, and we can still calculate the partial pressure of oxygen, or any gas for that matter. It's just the total pressure times the percentage of the air that's made up of that gas. And so with oxygen, it's always going to be total pressure times approximately 21%. Now, why is this such a big deal? Well, there's a couple of reasons. One, there's just going to be less oxygen, but two, the gradients change. Okay, so notice that if we start at sea level, inspired air is about 150 millimeters of mercury. By the time it reaches your alveoli, it's about 103. And then getting into your arterial blood, it's about 100 due to the AADO2, which we've talked about. And get into the venous blood, which is 60. So when venous blood returns back into your alveoli, we have a gradient of about 60 to 63. But if we go up to about 14,000 feet, notice that the gradients are very different, right? So inspired air is about 83, oxygen in your alveoli is only about 47, the AADO2 is widened a little bit, and that's because the gradient is reduced, and so it takes a lot longer for oxygen to diffuse out of the alveoli and into the blood. Okay, so even though we've got a smaller gradient, that slows down the rate of diffusion, and that causes a problem. So we can look at this by being on the oxyhemoglobin curve. So again, we have pressure on the x-axis and saturation on the y-axis. So as you can see, at sea level, we're about 98% saturated. We get to about 14,000 feet, and that's where we're on the shoulder of this curve, or thereabouts, maybe a little bit below it. Okay, so saturation's down to about 80%, and then if we're at about 23,000 feet, so still well short of Everest, now we're in the middle of that steep part of the curve. We can be down to about 50% saturation. So things are a little dicey. So when we're at altitude, the main thing is there's just less oxygen. Like, that's the big issue. Okay, and so as a result, exercise performance is decreased, and the percentage decrease, or the magnitude of the decrease, is dependent on how high in altitude you are. But it's important to remember that it's endurance performances that are affected. So those activities that start to rely on the oxidative systems. Okay. Now the way that we monitor this is we got those chemoreceptors in our carotid bodies, aortic arch, carotid sinus and aortic arch that monitor arterial pressure of oxygen. Now, when we get below 100 millimeters of mercury, we do have an increase in ventilation, but really it's not significant until we get closer to that 60, that pressure of about 60 when we get to the shoulder of the curve. And this is the main response that happens when we go to altitude. We just start breathing more. So the benefit of this is that hyperventilation increases our alveolar oxygen. And so when we get to a point where we stimulate that, we're going to hyperventilate. Okay, and we can see that here. So normal alveolar ventilation is right in here. It's about 4.2 liters a minute. Not a number that I would expect you to remember, but just to kind of give you an idea, if we use this when our alveolar ventilation is about 4.2 liters a minute, our pressure is at 100. So if we hyperventilate, it's going to go up. If we hypoventilate, it's going to go down. But notice we eventually get to a point where it kind of flatlines, right? So ultimately, we increase our alveolar ventilation, we're going to have a higher alveolar oxygen. Okay? So the benefit of this is that it increases saturation. It does this a couple of ways. One, we're just bringing in more oxygen, but we're also causing a left shift of the curve, right? So by breathing more or hyperventilating, we're decreasing the amount of CO2, we're decreasing the acidity, and so we have this left shift, which makes it a lot easier for oxygen and hemoglobin to bind. it's another one of those things that I like pointing out, where it's just the design of our body is such that, hey, I've got low oxygen, I start to breathe more. The act of breathing more brings in more oxygen, but the act of breathing more actually makes it easier for oxygen to bind to hemoglobin. Okay, but even though we hyperventilate, we're never going to hyperventilate enough to get our pressure back up and our saturation back up to normal. So how does this all affect exercise and exercise training? Well, so this is just normal sea level information, right? So red is before training, blue is after training. Now these lines should essentially be overlapping, but if I had them overlapping, you couldn't tell. So just assume that they're overlapping, but notice that after training, we have a higher cardiac output, right? And so our max cardiac output is higher, and really probably what should happen is that we don't have this last data point. So if we do the same thing with altitude, notice that if we go to altitude, we hit a cardiac output max earlier. Okay, so we'll hit the same max, but it occurs at a lower intensity. And so any submaximal exercise intensity causes us to have a greater cardiac output for a given workload. And this occurs due to an increased heart rate. We're trying to deliver more oxygen. So altitude itself doesn't change our cardiac output or our max cardiac output, but because we're at a higher cardiac output for each intensity, we're going to hit that maximum at a lower intensity. And ultimately what's going to happen is our VO2 max is going to be lower. Okay. So what's really weird about this figure is that the colors don't match up. So I'm trying to show you here. So right now I just want to focus on kind of the acute response. And so we're going to focus on this ventilation. So it says VE here, but it's this green line right here. So notice when we first go to altitude, we have a huge spike in ventilation, but it only lasts 5 or 10 minutes. And then after that, it starts to decrease. And then gradually over the next several days, it increases, right? And so the question is, well, what's causing this? And the answer is low oxygen causes us to breathe more. We start to hyperventilate, okay? And it's hyperventilation because we're breathing more than what we need for metabolic demand. And remember, we tie that metabolic demand to our carbon dioxide. We're not producing more carbon dioxide at altitude, but we're breathing more. And so what happens is our carbon dioxide decreases. And so we lose that drive to breathe. And so we believe that that's what causes this decrease, what we call the hypoxic ventilatory decline. And then kind of over time, we kind of find this happy medium and we gradually increase to try and have to increase our alveolar oxygen. Okay, and so we can see that see it from this picture as well, or from these figures here. So let's go through each of these. So on the x-axis here, we have alveolar oxygen. On the x-axis up top, we have saturation. And on the y-axis, we have ventilation. Notice we've got two different lines here. So the curved line is alveolar oxygen. The straight line is saturation. So notice that when saturation is really high, which corresponds with the high alveolar oxygen, we have a low minute ventilation. Okay, but as either of these values decrease, which are related, then our alveolar ventilation will really increase. Okay, similarly, we get to altitude, we have a huge increase over the first 10-15 minutes, and we have that hypoxic ventilatory decline. And we can see that at the same corresponding, we have a decrease in alveolar CO2. And these are different units here that are 0, 5, and 10. They're in something called kilopascals. Over here on the right is where we got the millimeters of mercury. Okay, so we breathe a lot, CO2 declines. We start to breathe a little bit less, it increases a little bit. And then as we have this greater increase over time, CO2 kind of flatlines. Okay, similarly, oxygen decreases. And that's just because we're at altitude. We kind of find this low point, and then gradually we increase until we get to wherever we're at. Okay, so in this case, oxygen, we're very hypoxic. Oxygen's what, 55, 60 there. And so with that, we will end the acute responses to hypoxia. And we will finish off by talking about chronic responses to hypoxia.